Good morning, everyone. Welcome to our presentation. Today, we are excited to share with you our work on UV spectroscopy. I am pleased to introduce our topic, UV spectroscopy, a powerful analytical technique used in pharmaceutical analysis. In this presentation, we will cover the fundamentals of UV spectroscopy, its applications, and how it is utilized in our field. We hope you find it informative and engaging. Let's get started. Let's talk about the principle behind this technique. Essentially, it involves the measurement and interpretation of electromagnetic radiation. This radiation is either absorbed or emitted by molecules, atoms, or ions in a sample. The key idea here is that these particles move between different energy states. When they do, they either absorb energy, moving to a higher energy level, or emit energy as they return to a lower level. By studying these changes, we can gain valuable insights into the composition and structure of the sample. This principle forms the foundation for many spectroscopic methods we use in analytical chemistry. It's all about understanding how energy transfer at the atomic or molecular level reveals the identity and concentration of substances. Now, let's take a closer look at some fundamental laws that govern light absorption. First, Beer's law. This law tells us that the amount of light absorbed by a material is directly proportional to its concentration. In other words, the more concentrated a solution, the more light it will absorb. This relationship is crucial because it allows us to determine concentrations simply by measuring how much light passes through a sample. Next, we have Lambert's law. This one states that the amount of light absorbed is proportional to the thickness of the absorbing material. So, the thicker the sample, the more light it absorbs. Both of these laws are essential because they help us understand and predict how light interacts with different substances. And, as you'll see later, they form the basis for many analytical techniques in chemistry and physics. They connect directly to our broader theme of understanding material properties through light behavior. Now, let's take a closer look at the different types of light sources commonly used in instrumentation. First, we have hydrogen discharge lamps, which are known for their strong emission lines in the UV range, making them useful for specific spectroscopic applications. Next is the deuterium lamp, which also emits in the ultraviolet region, but with a different spectral profile, providing a stable and continuous source for UV measurements. Moving on, the xenon arc lamp is a broad-spectrum light source that mimics sunlight quite closely, perfect for applications requiring a wide spectral range. Then there's the tungsten halogen lamp, widely used for visible light spectroscopy because of its stable and intense output in the visible and near-infrared regions. All these light sources are integral parts of the overall instrumentation setup, which typically includes several components. The light source itself is the starting point, providing the illumination necessary for measurements. Then, we have filters and monochromators, which serve to isolate specific wavelengths of light to analyze particular features of our sample. The sample cell is where the actual interaction between light and the sample occurs. After that, detectors measure the transmitted or emitted light, converting it into electrical signals. Finally, the recording device captures and stores this data for analysis. Each element plays a crucial role in ensuring accurate and reliable spectroscopic measurements, and understanding the different light sources helps us choose the right one for our specific research needs. Now, let's take a look at the xenon lamp. While our focus today is on various types of discharge lamps, I want to start by mentioning the hydrogen discharge lamp, which is quite fundamental. In this type of lamp, a pair of electrodes is enclosed within a glass tube filled with hydrogen gas. When electricity passes through, it excites the hydrogen atoms, producing a specific spectrum useful for various applications. Moving on to the deuterium lamp, which is a close relative but with a key distinction. Deuterium lamps are primarily used for ultraviolet spectroscopy because they emit a broad, continuous spectrum in the UV range. They're especially valuable in scientific research, where precise UV light sources are needed. Overall, these discharge lamps, whether hydrogen or deuterium, play a crucial role in spectroscopy and analytical techniques. They provide specific and stable wavelengths, making them essential tools in many scientific and industrial settings. Now, let's delve into the fascinating world of reflective grating monochromators. There are two main types of gratings we typically encounter: diffraction gratings and transmission gratings. Diffraction gratings are probably the most well-known. They work by bending light waves through diffraction, which allows us to separate different wavelengths effectively. Transmission gratings, on the other hand, allow light to pass through them, also dispersing the light into its component wavelengths, but in a slightly different way. Both types are essential in monochromators, which, as you know, are devices that convert polychromatic, or multiple-color light, into monochromatic, or single-color light. This process is crucial in many applications where precise wavelength selection is needed, such as spectroscopy or optical analysis. So, understanding these grating types helps us appreciate how monochromators achieve their high level of spectral purity and accuracy. Let's talk about transmission gratings. These are optical components that are used to diffract light into its component wavelengths, essentially acting like a prism, but with a different mechanism. They consist of many closely spaced lines or grooves on a transparent substrate. When light passes through, these grooves cause interference, separating the light into different directions based on wavelength. The key point here is that transmission gratings are highly efficient for dispersing light, making them incredibly useful in spectroscopic applications where precise wavelength separation is needed. They offer high resolution and are often preferred in situations where compact and lightweight components are essential. What's particularly interesting is how they connect to the overall theme of optical systems, improving measurement accuracy and enabling detailed analysis of light sources. By carefully designing the groove spacing and profile, we can tailor these gratings for specific wavelengths or spectral ranges, enhancing their versatility in various scientific and industrial settings. So, in essence, transmission gratings are fundamental tools that allow us to dissect light with remarkable precision, helping us better understand the properties of different light sources and materials. Let's take a closer look at filters today. When we talk about filters in radiation, we're essentially discussing tools that help us select or block specific wavelengths or types of radiation. Now, there are different types of filters, and two main categories are particularly important: absorption filters and interference filters. Absorption filters work by absorbing certain wavelengths of radiation while allowing others to pass through. Think of them as a kind of selective sponge that soaks up unwanted parts of the spectrum. They're often made from colored glass or gelatin, and they're quite effective in specific applications where you want to block out particular wavelengths. On the other hand, interference filters use the principle of interference. Think of thin film coatings that reflect certain wavelengths while letting others pass through. These are highly selective and are commonly used in more precise optical systems, like in spectroscopy or in cameras, to enhance image quality. Understanding these filters and their functions is key because they help us control the radiation reaching a sensor or a detector, which is crucial for accurate measurements or imaging in various scientific and industrial applications. So, whether we're absorbing or reflecting unwanted radiation, these filters are fundamental tools in managing the quality and clarity of the signals we work with. Now, let's take a look at sample cells, also known as cuvettes. These are essential tools used to hold the sample solutions during analysis. Think of them as tiny containers that keep our samples steady and contained so we can accurately measure their properties. It's important to choose the right type of cuvette because factors like material and size can affect the readings we get. When working with different samples, always handle the cuvettes carefully. Clean them thoroughly to avoid contamination and ensure precise results. In the context of our overall process, these sample cells are crucial because they serve as the interface between our sample and the measuring instrument, helping us obtain reliable data. Now, moving on to detectors, which are essential components in our measurement systems. When it comes to types of detectors, there are a few key ones to keep in mind. First, we have the photomultiplier tube, which is highly sensitive and capable of detecting very low levels of light. Then, there's the photovoltaic cell, which converts light directly into electrical energy, making it useful for various applications. Lastly, we have phototubes, which are similar to photomultiplier tubes but might differ in design and specific use cases. Understanding these detectors helps us choose the right one for accurate and efficient measurements, aligning with our overall goal of precise detection in optical systems. Now, let's turn our attention to phototubes and the fascinating world of photovoltaic cells. Phototubes are devices that convert light directly into electrical signals, which makes them incredibly useful in various applications like optical communication and light detection. Moving on to photovoltaic cells, or solar cells, these are specifically designed to harness sunlight and turn it into usable electrical energy. The key point here is that they operate based on the photoelectric effect, where light photons excite electrons, creating an electric current. This process is fundamental to renewable energy technologies and helps us understand how we can generate clean, sustainable power. By understanding the working principles of photovoltaic cells, we see how they connect to the broader theme of harnessing natural resources for energy production. They exemplify innovative ways to convert sunlight directly into electricity, aligning perfectly with our focus on sustainable energy solutions. Now, moving on to slide 12, let's take a closer look at the double-beam UV visible spectrophotometer. This type of instrument is designed to improve accuracy by simultaneously measuring the sample and reference. It essentially uses two beams, one passes through the sample and the other through a reference, allowing us to compare the two directly. This setup helps to minimize errors caused by fluctuations in the light source or detector, making it more reliable for precise measurements. In comparison, earlier, we discussed the single-beam UV visible spectrophotometer. While the single-beam instrument is simpler and more common, it measures the sample against a baseline, and any instability in the light source can affect the readings. So, the double-beam system's main advantage is its ability to provide more consistent and accurate results, especially useful in research and quality control, where precision is key. Understanding these differences helps us select the right instrument for our specific needs, ensuring our data is as reliable as possible in our overall analytical work. Now, let's look at some of the practical applications of UV spectroscopy. First, it's quite useful in the detection of impurities in various samples. By analyzing the absorption patterns, we can identify the presence of unwanted substances that might affect the purity or quality of a compound. This makes UV spectroscopy a valuable tool in quality control processes. Next, we have structure elucidation of organic compounds. This is where UV spectroscopy truly shines. It helps us determine the structure of organic molecules by analyzing their characteristic absorption patterns. These patterns give us clues about the electronic structure and the nature of conjugated systems within the molecule. Overall, UV spectroscopy is a powerful technique that not only helps us identify and quantify substances, but also provides insight into the molecular structure. Whether it's detecting impurities or elucidating complex organic structures, understanding how UV light interacts with molecules is key to advancing our knowledge in chemistry and related fields.